Welcome to Lesson 7 on continuity from the complex analysis class. We're going to define continuity for complex functions, but first we'll give an example of continuity for real valued functions and then build off of that. We'll prove a few theorems related to continuity, and we'll also provide a few examples in this lecture. The definition of a continuous function at a point is based on the definition of a limit. If the limit, as you approach the given point, in this case z sub 0, of a function equals the value of the function evaluated at that point, then the function is said to be continuous at z sub 0. This definition implies that f of z sub 0 is defined. And here we have an example of a piecewise function which is not continuous at a given point. We see here f of z is defined to be z squared everywhere except at 0, where at 0 we kind of alter the value and say it's equal to I, and that causes a problem because the limit of f of z as you approach 0 is 0, but the function at 0 is as we defined it here, is I, so the two don't equal. The limit doesn't equal the value of the function, and therefore the function is not continuous at z equals 0. From the previous lesson, the theorem 118, we showed that the limit of a polynomial at any point is equal to the value of the polynomial at that point. So all complex polynomials are continuous at every point, which gives us a fairly large set of continuous functions to work with. On this slide we have a variation, or an extension, I guess I should say, of a theorem from a previous lesson. In lesson 6 we proved that f of z broken down into its real and imaginary part has a limit at a particular point if and only if the limit exists for the real part and the imaginary part. And we can extend that to say that a function is continuous at a given point if and only if its real part and its imaginary part are also continuous at that same point. So just to write it out a little bit more formally, and I'll highlight where we made the extension here. The original theorem 116, we had the limit of f of z equals w0, where w0 didn't necessarily equal f of z sub 0. For continuity, we need to have this equality here. But once we have that, and then we break it into the real and imaginary part, this limit exists if and only if the limit of the real part equals the real part evaluated at the point x0, y0, which is z, and the same thing for the imaginary part. And we'll do an example in the next slide to show how we can use this. Okay, we have a few examples of the theorem I mentioned in the previous slide. First example, we have f of z equals e to the z, and we can break that into e to the x times e to the iy. Using Euler's formula, we have this expression and we multiply it out. And we have this real part here, which we know to be continuous from basic calculus. And in fact, I'll go over the associated theorem on the next slide. And the imaginary part, we also know to be continuous from basic calculus. So we can conclude from the theorem on the previous slide that f of z is in fact continuous at all points. Here's a second example. F of z equals z squared plus the conjugate of z. We expand that out and we get these two functions here. This one is continuous from calculus, and this imaginary part is also continuous. The interesting thing here, which we can't prove right now, we'll get to later when we define derivatives, but the derivative, even though this function is continuous everywhere, the derivative does not exist at any point at all. Concerning the first example from the previous slide, I stated that the real part of the function and the imaginary part were both continuous from basic calculus. And the theorem that gives you that is here from another book, or actually an online book. I put the reference down here, but we know that the limit of e to the x as x approaches some value is e to whatever that value is, and the same for cosine. We know these are both continuous functions, and so their limits exist. And if we just take e of x to be the f of x here, and cosine y to be the g of xy, then this theorem says the limit of the product equals the product of the individual limits. So we know that this is continuous from this part of the theorem, and we can do the same thing here for the imaginary part. Composition of functions. So if you take a function, say f, and for its argument you put in another function g, then we have what's called a composition of functions. We write it as f of g of z, and then this is perhaps more expressive. You have here f, and then instead of z you plug in g of z for the argument. And there's one catch here. G of z maps to a particular codomain, and if that codomain doesn't intersect the domain of f, then you don't have a defined function at all. So the codomain of g at least needs to intersect the domain of f, and that intersection is basically the domain of the composition of f of g of z. We have an example here. F of z equals x cubed, g of z equals e to the z. There's no problem with matching up the domains and the codomains here, because both of these functions are defined over the entire complex plane. So f of g of z, written this way here, we put in e to the z for g of z, and then we plug that into the formula for f of z. We get e to the z cubed, which is e to the 3z. If you do it in the opposite order, you're going to get something different normally. G of f of z, we plug in f of z for x, in this case z cubed for x, for z, excuse me, and then you get e to the z cubed. So these two things are different, but they're both well defined, it's just they're not the same function. The composition of continuous functions is continuous. So to prove that, we'll assume we have functions f of z and g of z that are continuous in over a set S, and we'll take any point z sub 0 in this domain of the composition and take any epsilon greater than 0. Okay, so by assumption, w sub 0 equals g of z sub 0 is in the domain of f, and f is continuous at this w sub 0. So by definition of continuity, there exists a delta prime such that f of w minus f of w sub 0 is less than epsilon whenever the modulus of w minus w0 is greater than 0 and less than delta prime. And we note that the modulus of w minus w0 is equal to, by definition, g of z minus g of z0. Now, in turn, since g is continuous at z sub 0, there exists a delta such that the modulus of g of z minus the modulus of g of z sub 0 is less than delta prime whenever the modulus of z minus z sub 0 is less than delta and greater than 0. So notice here what we normally call epsilon, we're using the delta prime. So if you put these together, we get what we need. Linking these statements together, we have that the composition of f of z minus the composition of f of z evaluated at z sub 0, taking the modulus of that, which equals, by definition, this expression here, which in turn equals f of w, because of the way we define g up here, minus f of w sub 0, and that's less than epsilon whenever the modulus of z minus z sub 0 is less than delta. And so that just traces back through the two steps that we have up here. We have one last theorem before we conclude this lesson and go into derivatives in the following lesson. If a function f of z is continuous and non-zero at a point z sub 0, then f of z does not equal 0 in some neighborhood, some open disk about that point. And just by the way, I'm using this labeling C2 just for continuity, theorem 2, and the previous one was theorem C1. I don't have these theorems in the book that I've referenced, the book that I had written and I made available for the listeners. So I needed to give some alternate numbering for a few theorems here and there that I'm adding just for the lecture, the videos, and not in the associated book. So that's the reason for this numbering here. So getting to the proof, it's pretty straightforward. We can pick any epsilon greater than 0. We'll pick this particular value here, the modulus of f of z sub 0 divided by 2. Since f is continuous at z sub 0, there exists a delta such that we have this expression here, or this statement here, which is basically the definition of continuity. We assume there's a z sub 1 in this neighborhood about z sub 0, such that it equals 0, so it's by way of contradiction. And then since z of 1 is within this neighborhood here, then this inequality holds if we put in z sub 1 for z, and we get f of z sub 1 minus the modulus of f of z sub 1 minus the f of z sub 0. This equals 0 from what we set up here. So this just equals the modulus of f of z sub 0, but then that's less than e, epsilon. And so we get a contradiction. We can't have this equal to less than half of itself. And therefore the theorem is true.